Hello, everyone. My name is Becca. I'm a director of product management here at NVIDIA. As Jack mentioned, I run our HPC software team, as well as our core math libraries. And so we're actually going to be spending a little bit of time on those today, given that we're going to be discussing HPC. So to start, we're going to be looking at two main themes for NVIDIA HPC software today. Number one is our main HPC software stack, which includes everything within our HPC SDK. And number two is we're going to be discussing Python for HPC, just to showcase some recent updates and how you can access some of our HPC software in Python from NVIDIA. So to start, let's talk about our NVIDIA HPC software stack, specifically our NVIDIA HPC SDK. Now, NVIDIA provides a software product to support our programming models strategy, which is the NVIDIA HPC SDK, which you can see here behind me. Our HPC SDK provides everything that you need to program from the CPU to the GPU, and it scales your applications to the full system that's available to you. The HPC SDK supports all of the programming models that you can see here, which I'll be discussing in the next slide. And it also provides 4 compilers, which maximize the performance both for CPU and GPU applications, support x86, ARM, OpenPower CPUs, so you can use them anywhere. Now, along with our compilers, we include a large range of common libraries that you'll need, including our core C++ libraries, all of our math libraries, and communication libraries so that you can maximize where you're able to scale your applications. Lastly, the NVIDIA HPC SDK includes all of our profilers and debuggers to aid in your understanding of your application. And we'll be spending the rest of the section in my talk taking you through all of these core components of the HPC SDK, which you can see here. So now, when it comes to programming the NVIDIA platform, from a hardware standpoint, it's typically the GPU, the CPU, or interconnect. And you'll need to be able to program to all of those. Now, programmers are typically deploying on their PC, premise cluster, workstation, and beyond. And we know that we need to provide a way to program that is portable across all of these mechanisms. Our accelerated libraries are a way to help you enable integrating into the GPU across your applications. And then on top of that, we have a variety of programming models, such as these high-performing ones that are all the way on the left here, that are without extensions. And you can move all the way to the ones on the right, which is, of course, CUDA, which has been co-designed with the NVIDIA hardware so that you can get all of the features and performance out of your application. So to showcase some examples of what programming at each of these different levels looks like from the prior slide, here's some 3 examples of what it means for your application's potential, access to performance, as well as portability. So now starting from the left, we have STUDPAR, or Standard Language Parallelism Code, which is highly portable, and it highlights relevant application property. Then we have OpenACC in the middle, which is annotating parallelism and high-level mapping into hardware abstractions. And of course, we have CUDA all the way on the right, which is fully specialized for the GPU and allows you to get the most performance out of your application. Now, standard language parallelism, also what we call STUDPAR, is a key component for HPC programming and the NVIDIA HPC SDK. Since 2020, the NVIDIA HPC compilers has been supporting parallelizing and offloading standard C++ and Fortran. NVIDIA continues to invest heavily in the ISO languages, where we are an active member of the communities. We have ongoing developments in our HPC software compilers and are open sourcing a lot of our developments in LLVM. Now, to give you just a very brief summary of some of our most recent highlights for HPC compilers, STUDPAR, we have improved both unified memory mode and interoperability with OpenACC in C++. Last but certainly not least, our NVIDIA HPC compilers can now generate a single binary that is capable of parallel execution on either multi-core CPUs or GPUs using the STUDPAR programming model. Now, more and more developers are using C++, have discovered the productivity and performance advantages of using ISO standard C++. And those interested have a growing list of open source examples, which you can reference here. Some of them we'll actually be discussing in a little bit. Now, to showcase just one example of how some of our OpenACC efforts, along with the interoperability with CUDA, has real impact, we're going to take a look at ICON. Now, ICON is a numerical weather prediction model developed by the German Weather Service, DWD, and it's used for forecasting weather and climate modeling. Now, ICON is an application that uses OpenACC and Fortran and has utilized our recent interoperability with CUDA, specifically CUDA graphs, which has GPU-enabled their code and optimizes GPU utilization by building reusable task graphs. Now, by ICON being able to combine both CUDA graphs and OpenACC, they have fused many small OpenACC kernels into a single graph launch, which has greatly reduced overheads. This result was a 7.5x improvement for certain phases of the application and roughly an overall 10% improvement in the whole application runtime. OpenACC and CUDA, along with their interoperability and joint optimizations, are continual focus areas for us here at NVIDIA, whereby we can embed OpenACC and CUDA to further accelerate all of your applications. Now, the HPC compilers are fully featured compilers for the NVIDIA platform. We have NVC, NVC++, and of course, NVFortran. Now, these compilers are great for accelerating all of your HPC applications on our latest GPUs and provide unmatched flexibility in choices for how to do that, from CUDA to OpenACC to STUDPAR. Now, besides GPUs, these HPC compilers are also optimized for CPU compilers. And all of this performance and optimization effort is applied across many of our platforms, targeting multiple generations of NVIDIA GPUs and both ARM, x86 to 64 CPUs. Now, to showcase an example of the NVIDIA HPC compiler recent improvements, we're going to take a look at NEMO, the Nuclear for European Modeling of the Ocean, which is a state-of-the-art modeling framework that is used for research activities and forecasting services in both ocean and climate sciences. Now, NEMO is using OpenACC for GPU acceleration. But here, I'm actually going to focus on their use of our HPC compiler component. That's a part of our NVIDIA HPC SDK. Now, the performance that NEMO was able to see as a result of moving from the CPU to the GPU with our HPC compiler, specifically NVFortran, has resulted in an 84x speedup when moving all the way from CPU to GPU with unified memory. And if you would like to hear and see more of a deep dive into just how NEMO was ported to Grace Hopper with unified memory and their use of STUDPAR, as well as other HPC compiler acceleration techniques and details, please be sure to check out the talk listed below for Accelerating Science with our NVIDIA HPC compilers, which I believe is going to be on Friday. As a reference, I will have several on my slides notes for where you can see other talks to dive into some of the details that we won't have time to dive into today. This is just the first one that I'm calling out because it's pretty exciting. All right. Our HPC compilers continue to receive updates with each release, and following are just a small subset of some of the recent updates that you can access with our compilers to access both increased speeds, unified memory optimizations across all of our programming models, and of course, CUDA graphs for OpenACC and CUDA Fortran, which I mentioned earlier with ICON, as well as ways to seamlessly integrate with a core set of our libraries, such as NVPL, which I'll be discussing shortly. Lastly, another really important component that's available in our NVIDIA HPC SDK is HPC-X. HPC-X includes MPI and OpenSHMEM communication frameworks, and it supports CPU and GPU networking right out of the box. HPC-X increases your scalability and the performance for messaging communications and is always fully tested and integrated into each of our HPC SDK releases. All right, we're going to chat about some math libraries now that come in our NVIDIA HPC SDK. So as you heard Jensen probably mention in the keynote, we have over 400 CUDA-X libraries, I think over 900 if you include frameworks. And of those, close to 40 core math libraries and API extensions, with more to come. Now, all of the libraries and extensions that you see here in green are included by default in the NVIDIA HPC SDK. And the others are available to you as a standalone download that you can access through DevZone, PyPy, CondaForge, wherever you prefer downloading your libraries. So let's quickly chat about some of these HPC libraries in our SDK and their latest updates and improvements that you can access today. Now, we aim to provide a super rich set of libraries specific to Grace. We've taken all of the common library APIs like BLAS and packaged them up as well-tuned versions for Grace. For APIs that are available for the GPU and don't have a CPU counterpart, we adapted those and packaged them all under NVPL, NVIDIA Performance Libraries. Now, we are providing a pretty great experience and performance that is right out of the box, that is integrated directly into the HPC SDK today. And it's available as a standalone download as well. We have new updates that were just recently published for NVPL for performance, and we are moving NVPL from being in a beta state to generally available in the coming months. Now, managing computation and communication in a machine is very hard. Our multi-GPU and multi-node libraries enable you to run larger problems, and we handle the complexity of communications and distribution for you to scale your problems to higher levels. Now, from cuFFT MP, which is for large 2D and 3D FFTs, cuSolver MP, which is for large linear solvers, cuBLAS MP for really large BLAS operations, and most recently, cuDSS, which is a new public beta library for direct sparse solvers. Each of these libraries is easily accessible for you to scale your problems across GPUs and nodes while removing the difficulty of distribution and communications. So we basically took these rich set of libraries and have been working to expand them beyond the node. So not just running on one GPU or all the GPUs on a node, but running across all of the nodes on your system. Now, it's hard to write your own large 3D FFT and handling the communication effectively at the same time. So we took that and provided you with APIs to integrate into your application with us handling all of that complexity under the hood. There's also another talk this week that you can go to for advanced multi-GPU scaling. I highly recommend this as well. Now, a great example of an application that is utilizing just one out of our 3 multi-GPU, multi-node libraries within the NVIDIA HPC SDK is GROMACS. GROMACS is a scientific software package that is widely used for simulating biomolecular systems and plays a crucial role in comprehending important biological processes, which are important for disease prevention and treatment. Now, GROMACS can use multiple GPUs in parallel so that it can run each simulation as quickly as possible. Both NVIDIA and the core GROMACS developers have been collaborating over the past several years to continue building on a series of multi-GPU and multi-node optimizations, which you can see some of the results referenced on the screen here behind me. Now, while cuFFT MP GROMACS has been able to perform the required FFTs in a distributed way across all of their multi-GPUs within and across all of the compute nodes, cuFFT MP uses NVSHMEM, which is a parallel programming interface enabling fast one-sided communications. It can make efficient use of both intra and internode interconnects to perform the all-to-all communications required by your distributed 3D FFTs. Now, with the integration of this new functionality, specifically cuFFT MP, the GROMACS application can now compute multiple PME ranks in the simulation, providing dramatically enhanced scalability and performance. Now, another example of a really popular scientific application that is the most used science application on computers around the world, which are utilizing two of our other MP libraries in the NVIDIA HPC SDK, is VASP. Now, VASP is for atomic scale modeling. VASP is also a Fortran code app that has been used for decades. Tons of HPC software has integrated their code to accelerate their application. And once VASP moved onto the GPU, they started integrating and using more of our HPC software components within the SDK to help continue maintaining a single source of code and accelerating their overall performance. VASP continues to iterate over time to enable improved performance, and a recent notable addition has been their multi-GPU, multi-node library integrations. These integrations with both cuSolver MP and cuBLAS MP has greatly improved their speedups, both 8x and just over 30x in select cases. Last but not least, we're going to talk about developer tools within the NVIDIA HPC SDK. So we know that no software is created without tooling. And so one more critical component of our NVIDIA HPC SDK is that we ship our tools there as well. CUDA debuggers, NSight Systems, NSight Computes, and of course our profilers. Our debuggers are integrated into a variety of IDEs, which include Visual Studio Proper and Visual Studio Code, right from the marketplace so that we can meet you where you probably already are. Our profilers are easy to use, and through our cuFFT interface, we can integrate with other third-party profilers as well. Now, it's interesting to note that our NSight Systems profile is able to scale to multiple nodes so that you're not limited to the performance on the GPU or just on a single node. You can analyze and look for hotspots on a multi-node application as well. And last but certainly not least, we have an exciting announcement for a private beta for NSight Copilot, which you can see in action today at the AI-assisted developer tools booth. The two NSight Copilots that you see here are directly integrated into the Visual Studio Code development environment and the NSight Compute kernel profiler. Now, NSight Compute, or NSight Copilot, is a suite of AI tools and solutions for CUDA developers. NSight Copilot will speed up and simplify your development, debugging, and optimization for all of your GPU-accelerated computing tasks. And all of these updates that you see here today will eventually be making their way directly into the NVIDIA HPC SDK as they come out of a private beta. Now, we know how important Python for HPC is, or we know how important Python is in the HPC community and how that's growing right now. So this next section is to give you a little bit of a quick overview of a few additional software components that we have available if you're looking for Python for HPC solutions. Now, at each layer of the NVIDIA platform, we have been building a ramp where there used to be a cliff, to help ensure that CUDA Python truly provides you with the first-class Python support that you're expecting. Now, we have a few deep dive sessions this week at GTC where you can go deeper into CUDA Python. But for today's session, I'm going to take you on a very quick journey through just some of our Python for HPC software solutions that are available to you today. So specifically, the libraries and framework, and you can see here in green, are going to be where we dive into even further with another update on Python-related dev tools so that we're continually ensuring to provide you with an end-to-end solution for you across the stack in HPC. All right, to start, NVMath Python, which is currently in a public beta, is one of our newest math libraries in Python, and it provides core numerical domains for science and AI for the Python ecosystem. Now, NVMath Python provides you with intuitive APIs that are designed for usability without any performance compromise. NVMath Python also allows for auto-tuning. Specifically, our host API is advanced, stateful, provides logging support, and of course, auto-tuning, as I just mentioned. Additionally, NVMath Python is fully integrated with package memory pool and current stream for a true seamless experience, which we'll get to shortly. Now, NVMath Python is built on top of the NVIDIA core CUDA math libraries, which I referenced earlier. And because of that, it has all of the performance knobs that are being exposed Pythonically for you. Experiencing native speeds with JIT or just-in-time linking is possible with NVMath Python. Earlier, I mentioned NVPL, or our CPU NVIDIA performance libraries. And just want to reiterate here that NVMath Python also provides support for both GPU and CPU memory and execution spaces, which are backed by our NVPL libraries. Now, the low-level Python bindings in NVMath Python can ease the migration that you have from C++. It also reduces the maintenance burden on your projects. NVMath Python provides interoperability with popular tensor libraries. And that seamless interoperability with popular tensor libraries includes use of package memory pool and current stream, which I just mentioned earlier. There are multiple levels with which you can leverage NVMath Python based on the specific needs that you have. So to conclude, NVMath Python provides you with the flexibility, interoperability, and functionality that you need for all of your core math library operations in Python today. You can use NVMath device APIs from within custom kernels written in NumbaCUDA, or now even with NVIDIA Warp tile programs, which I'm going to be discussing in the next slide. NVMath Python is aimed at cooperating, not competing, so that we can empower the entire Python numerical ecosystem to access our core math operations so that you can focus on your goals in HPC and beyond. So, speaking of Warp, Warp is an open source NVIDIA framework in Python that has use cases across geometry processing, differential simulation, and accelerated models and training. Warp provides a super thin abstraction layer over CUDA so that you can write GPU simulation code in Python and have simple yet efficient interoperability with DL frameworks that allow for flexibility in combining simulation and AI methods. Industry applications for Warp cover CAE, or computed-aided engineering, simulation AI, robotics, just to name a few. Now, programming tensor core math units can be super difficult to integrate with user programming, and they typically can lose efficiency, which requires super careful management of data flow between units. So unlike pure SIMT or single instruction multiple thread models, tile-based programming allows you to express these operations on tiles that multiple threads can execute cooperatively, enhancing both efficiency and productivity. So as of Warp version 1.5, which was recently released, you can now access tile-based operations, which are aimed at providing a programming model that allow you to smoothly transition from SIMT to tile-based execution. This greatly reduces the need for manual indexing, shared memory management, and pointer arithmetic. Warp now leverages cuBLAS DX and cuFFT DX, which are only two of the many core math library device extension APIs that we have, to implement matrix multiplication and FFT tile operations. Now, combined with Warp's tile programming model, these NVIDIA device-side math libraries enable seamless fusion of the Tensor Core Accelerated Gem, FFT, and other tile operations. And with this approach, we can outperform traditional linear algebra or tensor frameworks by a factor of 4x for applications that might require dense linear algebra, such as robot forward dynamics. And cuPyNumeric is another Python HPC library available to you, which allows you to write code simply in Python with NumPy. So if NumPy is your go-to, cuPyNumeric might be of interest to you. cuPyNumeric does not require MPI code and is an aspiring drop-in replacement library for NumPy that just makes it super easy to scale to multi-GPU and multi-node at runtime. Now, to ensure your end-to-end workflow and tooling needs are met for both writing and running Python applications in HPC, we also have a few notable updates for developer tooling in Python. So we've published an accelerated Python user's guide on GitHub for DevTools. With cuFFT Python, you can collect your own performance data directly from Python. And we have an updated Jupyter Lab extension, which provides you with profiling cells execution using the NVIDIA NSight tools. Now, the Pythonic developer tooling updates don't end there. We also have Python profiling available, which gives you Python call stack samples and CUDA API backtrace, as well as the ability to see annotated code ranges built into popular frameworks and libraries such as PyTorch. All right, so to summarize, we went over our NVIDIA HPC software stack, which includes all that is within our NVIDIA HPC SDK and a subset of our Python for HPC software solutions, which are available to you. I referenced several products with which we have deep dive talks for you this week to check out, so you can go deeper into something like our HPC compiler acceleration techniques, utilizing the newest updates from math libraries on Blackwell, as well as advanced scaling out of your applications with communication libraries. So here's the list of the GTC talks that I referenced throughout today's presentation. Happy GTC. I'm sorry if I spoke extremely fast for everyone, and thank you for your time.
So we have some time for questions. I'm going to bring the mic to you.
Give your name and thank you. Chris Powell, Chief Scientist at SAIC. A lot of what you spoke to was speaking to processing scale, and I'm also curious about data scale, particularly higher order tensors, 5, 6, and above, and also a lot of the data that we work with in HPC is typically petascale, and really wanting to see approaches that can help us perhaps with graph getting to truly exascale data and beyond for some of our more difficult problems. Also wrapped into that is questions about mesh generation and other types of things in order to deal with that higher order level of data.
And what are you using today?
Well, we're doing the best we can with the resources we got, right? So in any of the different, types of material sims or nuclear sims or other types of things, you use large-scale HPC x86 typically clusters, but really also wanting to expand the use, to get into some higher order potential applications and, more runs faster and things like that from that standpoint.
Okay. I don't have specifics on exactly what we might be working on today that could help answer your question, but I might have an expert that I can bring to a conversation after. So we should connect right after this, and I'll bring a subject matter expertise. Thank you for asking.
David Keys, KAUST, extremely impressive support beyond the CUDA ecosystem. Thank you very much for all those updates. One thing that seems omitted that would probably be quite low-hanging fruit is iterative linear solvers. You discussed many direct ones. Of course, users don't have a lot of trouble writing those themselves using your components as low-level, subdomain preconditioners and other things. But I'm wondering, isn't that something that would be fairly easy to add on just above the others? And do you have any plans of that nature?
The short answer is yes and yes. I mentioned it very briefly on one of the slides, and I just don't think it was in green, so it's not included currently in our HPC SDK stack. That doesn't mean it won't necessarily make it there, but yes to your question on we are working on that, and we should discuss some of your specific use cases because we might have something in the works that we should connect on after this. So yes, thank you, great question.
Thank you. Additional questions or comments? Here.
Hello, thanks for the amazing talk. My name is Dmitry Borzov. My name is Dmitry Borzov from WRC. So I was wondering, there was a lot of, in terms of the hardware, there is a lot of, for GPUs, there is a lot of support of the low precision numbers. So I was wondering if all this amazing work that you do, whether it's possible to leverage all this very high flops for the low precision numbers.
Yeah, so your question is whether everything that I mentioned in our NVIDIA HPC SDK can support some of the newer low precisions?
Yes, exactly. And then if it is, where can I, what are the keywords? How can I find more about this?
So I would highly recommend coming to our Accelerating Math Libraries talk on Blackwell, which is today at 2. We have some really great updates that are coming within cuBLAS specifically for some lower precisions that are going to be available on Blackwell. As soon as we have a newer updated release for the HPC SDK, where all of those are supported within our libraries, they are going to be coming to the HPC SDK as well.
Thank you.
Yeah.
Ross Miller, Oak Ridge National Lab. You talked a lot about cuPi numeric, and I think I saw a reference to cuPi on one of the slides. I'm just kind of curious, what is the relationship now? Does cuPi numeric supersede cuPi?
That's a great.
How's that all work?
Yeah, that's a great question. I don't believe we have someone from the cuPi numeric team here, but we do have a booth. Someone's name is Bo Dong. I can introduce you after. I can walk you over there, and we should discuss exactly. I just don't want to speak on behalf of that product because I'm not the subject matter expert, but that's a great question. Thank you.
Hi there, I'm John Taylor from ANU. I'm just interested in languages and language translation. So you're showing support for multiple languages, and you also have now got copilot into, is it the Python or CUDA development toolkit? What would be really useful is the ability to translate easily between languages. I think this is something that we need to be able to do so that we can move easily from one environment to another. So have you put any thought into language translation?
Yeah, specifically which or is there something specific within that you're looking for?
Well, taking some of our legacy codes in Fortran, moving them to Python, or vice versa, if we decide we want more performance out of our Python codes. It just seems like we're ready to be able to move easily. Languages have been a major barrier for people to move, and also to move on to new hardware. The languages tend to trap people.
Yeah, we don't have a solution for that today, but this most definitely is something of interest, and we're discussing it internally, but I don't have anything to share at the moment that would be available to you. But yes, that is most definitely something that we're looking into, especially in this space. Yes.
Additional questions or discussion?
Oh. It's a way to end
Mississippi
things.
State University. I was just wondering, the performance libraries, MVPL, are those only for the Grace platform, or are those optimized across all the products?
Yeah, they'll be for all of our CPUs. So for right now, that's Grace.
Yep. Okay.
Yeah. There's one more in the front. I don't know. Sorry, I'm just gonna. Yeah, go ahead.
Hi, Mark Ostrut, Simple Rose. Yeah, I have a question about NVCC. I'm wondering if there's any plans to parallelize computation or parallelize compile time in the future with NVCC. It might be a hard question, but it is a thorn in my side.
I think you probably have the same answer that I might end up sharing, which is I don't have that answer for you.
Thank you.
We do have some HPC compiler experts here that we can introduce you to, and yeah, we can discuss after. But great question.
It's a classic question from 20 years. Any other discussion for this tremendously vibrant session? So we value your feedback. Becca values your feedback. So use our stuff and put it in use, and let's move forward.
We know I spoke fast. You don't have to say that in the feedback. So.
Yeah. Thank you very much.
Thank you, everyone.